Today, our topic is, so in PSOC, our topic is uncompensated transmission. So last class we discussed, okay, so reactive power compensation. So, okay, so reactive power compensation and voltage. So why you want to maintain voltage will be constant, and some advantages and disadvantages of different compensation techniques and load compensation and specification of load compensation. So today our topic is uncompensated transmission line. Okay, so in uncompensated transmission line, so a transmission line will be characterized by four distributed circuit parameters. So actually the circuit parameters will be resistance, inductance, capacitance and conductance. So the characteristics behavior is dominated by L and C. Here inductance and capacitance will be dominated. So will be dominated the characteristics. So here Fernandes effect. So the Fernandes effect means the receiving end voltage will be greater than the sending end voltage. This is a Fernandes effect. So we have to calculate the here receiving end voltage by by placing a capacitor at the receiving end. So here the capacitance will be lumped at the receiving in the circuit. You have to see here the capacitance will be lumped at the receiving end. So in the circuit is equal to so actually current equal to V by R. So here V by here reactance equal to 1 by j omega c plus j omega L. Here the capacitance will be small compared to inductance. So omega L will be negligible. So Is equal to j into Vs into omega c. So now receiving end voltage Vr equal to Vs minus of Vs minus of Is into j omega L. Okay, Is into j omega L. So here Vs into minus of Is means j into Vs into omega c. So j into Vs into omega c and j omega L. Okay, here j into j will be j square. So j square by value will be minus 1. So Vr equal to Vs into 1 plus here so Vs will be taken as common, then Vs into 1 plus omega into Cl. Okay. So the effect of line capacitance is caused to no load receiving end voltage to be more than the sending end voltage. So this effect becomes more pronounced as a line length increases. So so in no load the receiving end voltage will be more than the sending end voltage. So this effect becomes more to be pronounced to be line length will be increases. So this phenomenon is known as Fernandes effect. Okay. So power flow. So in power flow, the real power PR equal to Vs into Vr by X into sine delta. R equal to Vr by X into delta V. So the real power will be directly proportional to sine delta, and reactive power is proportional to delta V. Okay. So delta V across the line. So a method of achieving delta V equal to 0 by reducing the line reactance. So the line reactance will be reduced by adding a series reactance. Okay. So next compensated transmission lines. So in compensated transmission lines, so shunt compensation. Okay. So the shunt connected static wire compensation. Okay. So a shunt connected static wire compensation. Okay, composed of a thyristor switched capacitor and thyristor controlled reactor. Here shunt compensators will be TSC and TCR. So the compensators is normally operated to regulate the voltage of the transmission system at a selected terminal. Okay. Here the compensators will be normally placed at the transmission system at a selected terminal, often with an appropriate modulation option to provide a damping if a power oscillation is detected. Okay. So here we have to see shunt compensation, thyristor controlled reactor, TS. Thyristor controlled reactor, TCR. So static compensation using TCR will be absorbs the reactive power. It contains two main components. Those are thyristor and line reactor. Okay. So TCR, thyristor controlled reactor. So it will contain SCR and reactor. So that the circuit shown in below, it uses a filter and filter bank and reduces the harmonics generated in it. Okay. So the TCR absorbs reactive power. Okay. So it will be it reduce it filter back to filters and back to reduce the harmonics generated in it. In order to vary the current from 0 to maximum value is varied where is the firing angle. Okay, so this respond of the reactor. Okay, here the two thyristors will be connected opposite and reactor will be connected in series. Okay, so this is the TCR circuit diagram. So in order to vary the current from 0 to maximum value, so it is varied where the firing angle. So where the firing angle. Okay, so this respond of the reactor. Okay, next, thyristor switched capacitor. So here thyristor switched capacitor. So it contains two main components, thyristor switch and line reactor. So you have to see this circuit diagram. Here thyristor switched capacitors, voltage regulators and a control system. So here thyristor switched capacitors will be voltage regulator and a control system. Okay. So it will be regulate the voltage and it will control the system. Okay. Here TSC. So thyristor switched capacitors will be placed and here switch. So in HV compensation bus bar, the here the power here power transformers, here the power transformers will be connected to reference voltage regulator. So this voltage regulator will be connected on TSC. Okay, so here the power transformer, delta star transformer will be connected MV compensation bus bar. So this compensation bus bars will be divided into switching devices. So here the switching devices will be connected TSC. Okay. So this is a circuit diagram of TSC. Here the TSC will be connected, two opposite TCRs will be connected in series with a capacitor. So this is a TSC circuit diagram. Okay. So this TSC will be connected per power system. Okay. So the thyristor switch. So thyristor switch. Here this thyristor switch. Okay, so the thyristor switch from figure, it can be seen that thyristor switch consists of two SCR stacks. So this SCR is used in series in each stack and the number of depends upon the value of rated voltage of switch. So a step of transformer is necessary for connection to the network in order to complete the circuit of TSC. Okay, so SCR switches are used to switch and they cut the shunt capacitor unit. So to obtain a step change in a reactive power supply to a system. So reactor L is connected in series with a capacitor and used to control the rate of rise of current through the SCRS. So the operation is explained in two cases, whether the capacitor is on position and off position. So here the thyristor switch will be consist of two SCR stacks. So this SCR is used in series in each stack and number depends upon the value of rated of voltage of switch. So here the switch. So here the switch thyristor switches. So TSCs will be connected in series depending upon the value of rated voltage. So here by using a TSC we can control the voltage. So the step up transformer is necessary for a connection to the network in order to complete the circuit of TSC. So SCR switches are used to switch the SR switches are used. Why? Because it cut a shunt capacitor shunt units and to obtain a step change of reactive power supplied to the system. So it will be obtained step changing reactive power. So reactor L is connected in series with a capacitor and is used to control the rate of rise of current through the SR. So this operation will be explained in two cases, whether the capacitor is on position and off position. Okay. So when switching on a capacitor, so the capacitor will be switched on in TSC. So when the capacitor is on position, there are a changed there are there are charged at all times of peak values of frequency in order to obtain a transient free switching on the capacitor. So whenever the capacitor will be on, so it will be charged at all times to a peak values of frequency. So it will be charged at all times to a peak values of frequency in order to obtain the transient free. So it will be obtaining transient free switching on the capacitor. And whenever we will be switch off the capacitors, this can be achieved by the termination of firing pulses to the anti-parallel SCRs. When the current becomes zero, the SCR will be blocked. So now the capacitor will be charged. So now the capacitors will be charged. Position for the next transient free switching. Okay. So switching off a capacitor. So the capacitor will be switched on whenever the anti-parallel SCS. So the firing pulses will be terminated. Then anti-parallel SCS when current becomes zero. So then the capacitor will be switched off. So the SCR will be blocked. So now the capacitor will be in charged position and the next in transient free switching. Okay. So drawback. So in this TSC, the drawback will be the drawback of series compensation method is that high voltage is produced across a capacitor terminal. So high voltage will be produced across a capacitor terminal when the short circuit current flows through them. So therefore, special protective capacitors are used under such a condition. Okay. So high, so it will be short circuit current flows through them and produces high voltage across a capacitor terminal. So this will in this condition we are using a special protective capacitors in such a condition. Okay. Next, series compensation. So in series compensation, the objectives of series compensation. So the effect of series compensation on the basic factor is determining the attainable. So the basic factors are determining the attainable. So that is maximal power transmission and steady state power transmission. So maximum power transmission, steady state power transmission, limit transition stability and voltage stability and power oscillator damping. Okay. So here limit transient stability and voltage stability and power oscillation damping. Okay, so in series compensation, the objectives of series compensation will be maximal power transmission, maximal power transmission, steady state power transmission, limit and transition stability and voltage stability and power oscillation damping. Okay. And next, concept of series capacitance compensation. So in the concept of in series capacitance compensation, the basic idea behind the series capacitive compensation is to decrease the overall effective series transmission impedance from the sending end to receiving end. So here the series capacitive compensation will be decreases overall effective series transmission impedance of the sending end to receiving end. So here such that x in this p equal to our b equal p equal to b2 by x into sine delta. So the relationship characterizes the power transmission over a single line. So here consider the simple two mission model with a series capacitor compensation line which for a convenience is assumed to be composed of two identical segments. Okay, here note that for the same end voltages of the magnitude of the total voltage across a series line inductance. Here series line inductance, the voltage Vx equal to 2Vx by 2 is increased by the magnitude of opposite voltages. So Vc is developed across a series capacitor and thus result from an increasing in the line current. So and series capacitive compensation, so the series capacitive compensation will be decreases the overall effect of series transmission impedance. So it will decreases the overall effect of series transmission impedance from sending end to receiving end. Okay, so here p equal to v by 2x into sine delta. So this relation will be characterized by a power transmission over a single line. So consider a two mission model with a series capacitor compensation line. When for a convenience, it is assumed to be composed of two identical segments. So here same the end voltage of a magnitude of total voltage across a series inductance Vx equal to 2Vx by 2 is increased by the magnitude and opposite voltage of Vc. It developed across a series capacitor. This results from an increasing the line current. Okay. So effective so here effective transmission impedance with the series capacitance compensation. So effective transmission impedance with a series capacitive compensation is XC effect equal to X minus XC. Okay, here X effective, so the reactance effective will be 1 minus K into X. Here Xc equal to K into X. So then we are taken as X will be common, then so effective so here transmission impedance with the series capacitance. So effective impedance X effect equal to 1 minus K into X, where K is the degree of series compensation. Here K is the degree of series compensation, that is K equal to Kc by X. Okay, so assuming the voltages Vs equal to Vr equal to V, so then the current of in a compensation line I equal to 2V by 1 minus K into X sine delta by 2, and real power transmitted Vp equal to Vm into I, and here Vm equal to V square by 1 minus K into X sine delta. Okay, so next reactive power supplied by a series capacitor QC equal to I square X. So here I square means 2V square by 1 minus K whole square into X and 1 minus of cos delta. So this is reactive power supplied in a series capacitor. Okay, so here the effective impedance for a effective transmission line. And next current compensation of line and real power transmitted and reactive power supplied by a series capacitors. So this is in series compensation technique. Okay. So that's it. Thank you.